So in the last video, it just cut off whenever I was saying that we're going to use 3 pi over 4. So our r theta would then be root 2 and then 3 pi over 4. So I'll go over 1.4-ish and I'll go around to 3 pi over 4. I'll land right there. Realize that there's infinitely many, like I was saying before, so you could also do negative 1.4-ish and go over this far, which would be 7 pi over 4. So you can make your r negative, and it would then be 7 pi over 4. So either of those will work. Now I have two that I want you to try. So do negative 2 comma 2 and then negative 1 comma root 3. Convert those to polar form. Make sure you think about the angle. Pick the correct angle because both of these are in quadrant 3. So you have to think about that. X is negative here. So let's get to the calculus of polar. Now we will be doing a little bit of graphing in polar because it's going to make the problems a lot easier if you understand how to graph. So this is a general intro, all this stuff. Now I'm going to show you what you have to do on the calculus exam with respect to polar here. So if you know these 4 things, oh, I didn't type the last one, hold on. So here are the 4 things, like I said. The first one, dr d theta. Remember, our polar functions, instead of being y equals f of x, they're always going to be r. The radius is a function of the angle. So instead of dy dx, I have dr d theta because r is replacing y, theta is replacing x. So dr d theta is going to express the rate of change of the radius with respect to the angle. So if dr d theta is negative, then the curve is getting closer to the pole. That would look something like this, getting closer to the pole. If dr d theta is positive, as I rotate, remember we're always rotating here, then I would be getting further away from the pole, something like that. So our radiuses, we're getting further and further from the pole. Next thing is slope. This is really similar to in parametric mode, how we said dy dx is equal to dy dt over dx dt, where t was the invisible third parameter ticking along in the background. Now we have dy d theta over dx d theta. It's a little bit more complicated in polar though, because to do dy d theta, y, remember, is r sine of x. So you have to take the derivative with respect to theta. That's what d d theta means. So d d theta of r sine theta. Dx d theta, you have to do the derivative with respect to x of r cosine theta, because x is r cosine theta. We'll be practicing that in class. Next thing is area. So let me show you a couple things to keep in mind. When we're doing area in polar, it's not the area under the curve, but it's the area swept out by a radial segment as theta varies. So what you're used to is you'll have some kind of function on the xy plane, and your area is under the curve, so between the curve and the x-axis. But that doesn't happen in polar anymore because we are going to be on the polar plane. In polar, whenever we do area, so we'll be rotating around something like this. Polar curves can really be anything. It's not the area under the curve because it's like, what is the area under the curve? It doesn't make sense. It's the area as you rotate around. So usually contained by the curve, or if theta starts here, here's your radiuses as you go around, and your angle is increasing as you go around like this. So it's a little bit different way of thinking about area. It's the area contained as theta varies. Next, what I meant to show you is in geometry, there's a formula. Let's say I have a perfect circle. There's a formula for area of a sector of a circle, and if it's perfectly circular, then you can find the exact area of this, and that area is 1/2 theta r squared. You might have seen this in geometry before, or hopefully you have. So that's the area for a sector. Now let's say I have a polar curve, and polar curves aren't, or they don't need to be perfect circles. Let's say something like this. So that's not a perfect circle. And let's say I want to find this chunk right here. Okay, so right in here. Now this right here is not an exact circular segment going around, but what we do, just like when we found area under curve, we split it up into a bunch of rectangles and the top was almost flat. You're going to split this up into a bunch of baby segments. And at each edge, if you make the segment skinny enough, then this right here is almost part of a perfect circle. Almost part of a perfect circle. And instead of dx being tiny, tiny, right here, it's your d thetas being tiny, tiny, tiny. So you're making d theta as small as possible. And then what you do is you add up a bunch of these little segments. So you add up a bunch of your 1/2 r squared d thetas. I'm using d theta instead of theta because it's tiny. And then you take the limit as the number of baby segments goes to infinity. So you could use n for the number of those. And remember, in calculus, we replace a limit with sigma with an integral. And that's how we get the integral. You take the 1/2 out front. You use d theta instead of theta. So again, limits are coming to the rescue here. Instead of adding up infinitely many rectangles, we add up infinitely many little sectors of a circle. So go ahead and write down that area formula. Lastly, we have arc length. So if I have some kind of polar curve going around and I want to know the length of the arc, let's say from here, from there to there, this is very similar to the arc length formula that you already know, 1 plus f prime of x squared dx. And then you know one for parametric mode, which was dy dt squared plus dx dt squared dt. Here's the one for polar. So you go from theta 1 to theta 2, 1 plus dr d theta. Instead of f prime, you do dr d theta squared. D theta. In polar, it's always d theta because it's the thetas that you make tiny, tiny, tiny. One thing, you can use theta 1 and theta 2. So let's say you start rotating. Here's your theta. Let's say you want to start at this angle. Theta increases, stop, and you want to end at that angle. You can call them theta 1 and theta 2. Or you can call them theta and alpha. Or you can call them theta and beta. So a lot of times college books won't use theta 1 and theta 2. They won't use a subscript. They'll use 2 different letters to represent angles, like alpha or beta. But I'm just going to use theta 1 and theta 2. I think it's a little easier to work with. So get all this stuff down. This is what we're going to work with. Next week we'll be graphing a little. We'll start some free responses so you can get a feel for how these are asked.
Hello, everybody.
I'll see you guys next week.